Assalamu alaikum. So, in this lecture, I will discuss with you uh, the term maximum torque per ampere, which means that how to select the reference current in the d-axis such that the torque is maximum with minimum current. So simply, the maximum torque per ampere, which for short we'll call it MTPA, is a constraint optimization problem which can be formulated as minimize the magnitude of the stator current, which equal IDS square plus IQS square, subject to the torque TE equal to 3 over 2 P over 2 lambda IQS plus LD minus LQ IDS IQS. So simply, if we assume that this is the QX and this is the DX. Now we know that the flux of the magnet is directed or pointed toward the D. So this is the lambda m, or virtually simply IF, the field, is pointing toward IDS. But you know that in the parent magnet we don't have actual field in the rotor. The rotor contains a magnet or parent magnet, which can be either surface mounted or inserted inside the rotor, which is the parent magnet rotor. And this one is constant. This one is constant. And if you recall, in the magnetic circuit, we said that we cannot increase the magnetic current or the magnetizing current, because the core will enter into saturation, and if the core is entering saturation, this means that you are consuming more current than you need, and this will generate heat in the core. So the only possible scenario is to if we need to impose any direct axe current in the negative side. So for that, let's assume this is the IS, and let's define this angle here as beta. So from here we can calculate the projection along the D and the Q. So this projection from here to here, which equal IQS, is equal IS cosine beta, and this projection is equal IDS, which represents the IDS, is equal to minus, because I'm injecting current in the opposite direction of the D, IS sine beta. So in the maximum torque per ampere, we need to find the component, the torque component and the flux component, such that the current is minimized and the torque is maximized, which is the maximum torque per ampere. which is what we call the maximum torque per ampere. So now let's substitute the value of the IDS and the value of the IQS in the torque and see what we can do with that. So simply now substituting, TE will equal to the constant, which is the 3 over 2 P over 2. Now here we have lambda m, and instead of the IQS I will use IS cosine beta, and here we have a plus IDS LDS minus LQS multiplied by IDS IQS. So here we have minus sign, so this will be minus. So this will be minus, and we have LD minus LQ, and we have IS square. We have cosine beta sine beta. Now cosine beta sine beta actually is 1 over 2 sine 2 beta. So now we can rewrite the torque TE equal to 3 over 2 P over 2 lambda m IS cosine beta minus LD minus LQ over 2 IS square sine 2 beta. So we need to find beta at which the torque is maximum, and for that we'll do partial TE respect to partial beta, and this will equal to 0. Now if we do the differentiation, we don't need the constant because in the end of the day those will be cancelled. So here we will have the first one is minus LM IS sine beta, and this one too will cancel the 2, and we will have minus LD minus LQ IS square cosine 2 beta. This must equal to 0. Now we know that cosine 2 beta, this one can be written as cosine beta square minus sine square beta. So if we do so, we'll end up, I don't need this minus, I can multiply all by minus, so I will end up with lambda m. Now IS sine beta plus LD minus LQ IS square cosine beta square minus IS square sine beta square. This must equal to 0. Now please note that IS sine beta is minus IDS. So this one here is minus IDS. And IS cosine beta, this one is IQS square, and this one is the IDS square. So now we can write it as, so this is minus lambda m IDS plus LD minus LQ IQS square minus LD minus LQ IDS square equal to 0. So I can multiply also by minus here because I need to solve with respect to the IDS, and I can also divide over LD minus LQ. So for that we will get IDS square plus lambda m over LD minus LQ IDS minus IQS square is equal to 0. Now this second order algebraical equation, it has a closed form. So if we recall, if we have a s square plus b s plus c equal to 0, the solution for s is equal to minus b plus minus the square root of b square minus 4ac over 2a. So simply a, b, and c. So a is equal to 1. So from here we have a is equal to 1, and b will equal lambda m over LD minus LQ, and c will equal to minus 1. So simply this means that IDS will equal to minus lambda m over LD minus LQ plus minus the square root of lambda m over LD minus LQ all squared plus 4IQ s square over 2. So this can be simplified to IDS equal to minus lambda m over 2 LD minus LQ plus minus the square root of lambda m square over 4 LD minus LQ squared plus IQ s squared. Now please note that the IDS must be either 0 or negative. It cannot be positive, because if IDS is positive, this means that the core will be saturated. So simply IDS must be less than or equal to 0. So for that I will take the negative sign here. So simply IDS for the maximum torque per ampere will equal to minus lambda m over 2 LD minus LQ minus the square root of lambda m square over 4 LD minus LQ squared plus IQS squared. So simply given IQS, we can calculate IDS in order to achieve the maximum torque per ampere. Thank you.